Hello everyone, welcome back. In this particular video, we're going to start talking about Claisen condensations. Claisen condensation is a reaction of esters that is analogous to the reaction of carbonyl compounds, and it involves the alpha carbon. So it is the equivalent of an aldol reaction, but involves esters as starting materials. And since this involves esters as starting materials, and this is analogous to the aldol reaction, what it means is you need an ester which would have alpha hydrogens in it. In fact, we will notice later that as we work through the mechanism, we're going to see that we want esters that have at least 2 alpha hydrogens for a reason. Okay, and so we are looking at the first reaction, or like an example here, where I have ethyl acetate essentially here. So this is an ester. So 2 molecules of this ester can condense to give what's called a beta-keto ester. Okay, this product is called a beta-keto ester. Now that's just a generic name, like a very generalized name for it, because when we think about the ester as our functional group here, this is our alpha carbon, and there is a keto group at the beta carbon. So that's why it's called the beta-keto ester. So for doing this reaction, you need a base, and the reaction is actually done in 2 steps. And you can see that here we are using sodium ethoxide as a base. And what's important to keep in mind here is that the base, you want the base to match with the alcohol part in your ester. Okay, so if you look at this part here, that's what we are using as the base here. And this is for a reason, so that we do not complicate things further, and we'll go through it as we work through the mechanism. Okay, so we do this in presence of a base, and the reaction is followed by an acidic workup or an acidification step to complete the process. And that would give us the beta-keto ester as our product. So let's look at the mechanism of this reaction. So the mechanism of this reaction, like all other reactions that would involve the alpha carbon, would start with the formation of an enolate. Since we are operating under basic conditions, the enolate is going to be our nucleophile. Okay, so if we start with this ester, and I'm going to draw the ester this way so that we can work with the alpha carbon. So that's our alpha hydrogen. Here's our alpha carbon. In presence of a base, this alpha carbon will get deprotonated, or the alpha hydrogen would get deprotonated, sorry. Okay, so the alpha hydrogen is going to go deprotonated, so the base can deprotonate this alpha hydrogen. Simultaneously, the electrons from this bond come to the space between alpha and beta, the alpha carbon and the acyl carbon, and the double bond here gets pushed up, such that we will get the enolate now. So we'll get the enolate where the oxygen has a negative charge. We have OET here and a double bond here. So that's our enolate. This is our ester. Now again, the pKa for this alpha hydrogen in an ester molecule, okay, this is less acidic than the alpha hydrogen in a carbonyl compound. So the pKa for this hydrogen could be somewhere in the range of like 22 to 24 pKa units. So it is less acidic. And along with this, when you make this enolate, we are going to make ethanol. The sodium ethoxide base, when it deprotonates, it's going to become ethanol. The sodium ion is going to be a counter ion for the enolate there. And the pKa for ethanol, again, to round it off, it's around 16. approximate pKa values. And so essentially what you notice is that there is a huge difference in pKa's here. So very similar to what we saw in the aldol reaction. And so what that means is this reaction does not, or this deprotonation is not favorable. You do not generate a lot of the enolate. You just generate a little bit of the enolate. The ester is still present at the as the ester at equilibrium. Okay, and in this particular case, this ester can be called the keto form because this is a keto enol tautomerization in some sense. Okay, so this is still the keto form, although it's not a keto functional group. So we can still call the keto form, and we've got the enolate. So once you generate some of this enolate, the enolate is nucleophilic at the alpha carbon. Okay, so we know that. So essentially what happens is this enolate is going to react with another molecule of the ester because there's more ester left behind. So if you look at the scheme here, I've put two equivalents of the ester, but it's not necessary to show that because it's some of the enolate that's generated reacting with the ester that's left behind. Okay, and that would basically push this equilibrium forward. So the enolate can react with the ester. Now the ester is a carboxylic acid derivative. This is an acyl carbon that's still electrophilic. So essentially what happens is the lone pair on the oxygen comes down, and the enolate can go and attack this acyl carbon with the simultaneous push of the double bond to become a lone pair on the acyl oxygen. So this is going to now give us OET, double bond O there. This is our alpha carbon, okay? And the alpha carbon is now connected to this other carbon, which has an oxygen with a negative charge on it, has the OET, and there is a methyl group here. That's what we get. Now, if you look at this, what we made here is a tetrahedral intermediate. Okay, and this tetrahedral intermediate is coming from a carboxylic acid derivative. So once you make the tetrahedral intermediate for an acyl carbon or for a carboxylic acid derivative, the next step is the collapse of the tetrahedral intermediate. So what's going to happen is this tetrahedral intermediate is going to collapse. Okay, so we're going to do the collapse here. So this is basically the collapse of TD or TDI, the tetrahedral intermediate. Okay, collapse of the tetrahedral intermediate happens. And as the lone pair on the oxygen comes back to become a double bond, the OET here is going to get kicked out. That's what gets kicked out. That's the leaving group, or that's the better of the leaving groups there. And so essentially that's going to give us C double bond O, OET, two lone pairs, the alpha carbon here, and we get a double bond there. And we'll have a methyl group. So notice how we've created the beta-keto ester. Okay, that's the beta-keto ester. And along with that, there's the ethoxide, the base that got kicked out. Okay, so we basically regenerated the same base that we started by the reaction with. So it might seem like this reaction is catalytic in base, but actually it's not. Because what happens is, once this beta-keto ester intermediate is formed, notice there are further alpha hydrogens here. In fact, two more for this particular case. And the pKa for this alpha hydrogen is, I would say, approximately in the 11 to 12 range, approximately in that range. which means the pKa for those alpha hydrogens have now dropped significantly compared to the ester where we started with. And given the pKa of ethanol or the pKb of the base, what that means is the base finds it easy to now deprotonate these alpha hydrogens, okay? So let me draw the arrow push, show good arrow push here. So these electrons, as the alpha hydrogen is deprotonated, go to that alpha carbon. And because of the huge pKa difference here, this reaction is favored in the forward direction. So in some sense, it is this deprotonation event that pulls this reaction forward, that makes this reaction feasible, because this deprotonation that we did for that alpha hydrogen is now very feasible. So that's going to give us ethanol. Again, pKa for ethanol is around 16. So you can see that the stronger acid is on the reactant side, the weaker acid is on the product side. That means this reaction is favored. So you get the enolate of the beta-keto ester. Okay, so that's where we end. So we've got the enolate now. So this is another enolate. Let me actually make some room for writing that. So this is the enolate of beta-keto ester. So we may make that, and plus we have ethanol, which is coming from the base, with a pKa of around 16. So that explains why this reaction would be favorable. Now, contrast this with the aldol reaction. In the aldol reaction, what made that whole reaction favorable was the formation of the alpha-beta unsaturated compound. So there was a stable compound formed there. So there, the stability of the compound pulls the reaction forward. Here, the favorable deprotonation of this beta-keto ester pulls the whole reaction forward. And when you do this, we are consuming the ester. So we are not, sorry, we are consuming the base that we are using. The ethoxide, although it seemed catalytic until this point, it is now used up for this final deprotonation to get the enolate. So this is where we are at the end of the first step. And so then when we do the final second step, which is the protonation event, okay, when we do the final protonation, this beta-keto, the enolate of the beta-keto ester gets protonated. And so that's going to then give us the product, which is the beta-keto ester itself. So that's how we get the beta-keto ester. So notice we make the beta-keto ester under basic conditions, but that beta-keto ester cannot survive under those basic conditions because it's going to get deprotonated. And you end at the enolate. That's sort of the resting state of the product under basic conditions. When we do the acidic workup, when we add the acid or do the protonation, then it gets converted into the beta-keto ester back. So that's how we get the product here. Now that we know the mechanism of a Claisen condensation, how a beta-keto ester product is formed starting from an ester under basic conditions, let's try to understand why the nature of this base or the identity of this base is important. And as I mentioned earlier, you want the base to match with the ester that you're using or the alcohol portion of the ester that we're using. You want these two to be the same. So in this particular case, we're using an ethyl ester. So our base is sodium ethoxide. If I use a methyl ester, the base must be sodium methoxide. Or if it's another ester, then the base should be matched with this part of your ester. Why is that? Why can't we use something like sodium hydroxide as a base? What's wrong with that? Let's look at that. And it is based on some understanding of the reactions of carboxylic acid derivatives that we previously know. So let's consider a situation where we are going to use sodium hydroxide as a base. So we have the ester and we have sodium hydroxide as a base. So with sodium hydroxide as a base, yes, sodium hydroxide is as basic as ethoxide, okay, almost the same. They have very similar basicities. So what sodium hydroxide can do is it can deprotonate the alpha hydrogen. Okay, it can come and deprotonate the alpha hydrogen, and it would give you the enolate. So it can give you the enolate here. So you can make the enolate. That's one possibility. Okay, this is the this is deprotonation of alpha hydrogen. That would give us the enolate. But sodium hydroxide is also a good nucleophile. So with a carboxylic acid derivative like this, especially an ester, another possibility is that sodium hydroxide, instead of deprotonating the alpha hydrogen, okay, instead of doing that, it can actually go and do an attack at the acyl carbon, because that acyl carbon is electrophilic. And when it attacks the acyl carbon, the double bond is going to open up. Okay, let me use the dotted electron pushes here. So it's going to open up. So we can consider another possibility where we have a nucleophilic acyl substitution. So we could have the nucleophilic acyl substitution happening. And so essentially this attack would give us a tetrahedral intermediate. Okay, and this process is, okay, there is equilibrium here. It's going to give us a tetrahedral intermediate. And when the tetrahedral intermediate collapses, one of the possibilities is that the ethoxide here gets kicked out. The hydroxide could also get kicked out, and that would take us back. But if the ethoxide gets kicked out, then it's going to take us to a carboxylic acid plus ethoxide. And since you have a carboxylic acid now with the ethoxide can go and deprotonate the carboxylic acid, and this would give us the carboxylate plus ethanol. So you see how there is complication involved here, because you have two competing reactions. You could have the deprotonation of the enolate of the alpha hydrogen to give you the enolate, but what you have to what's important to recognize is that this deprotonation is not favored. Okay, this is not a favored reaction because of the difference in the pKa's here. This is not a very acidic hydrogen, so it's not a very favored deprotonation that we are looking at. And so the major process is going to be this nucleophilic substitution. Okay, this is going to be the major pathway here, which gives us an unwanted reaction. So we don't have the ester anymore. We've made the carboxylate, and that may not undergo your required Claisen reaction. So that's what happens when we use the sodium hydroxide. Now, when you use another base, let's say your base doesn't match with the alcohol part in your ester. What's possible here is something similar to what we discussed here, because what can happen is, again, sodium methoxide would be able to deprotonate, but similar to here, that deprotonation is not a very favored pathway. So what we're going to get is we will have the ethyl ester, and if we use sodium methoxide along with it, then we are going to get what's called a transesterification reaction. So the methoxide can act as a nucleophile, attack the ester to give you the tetrahedral intermediate. When the tetrahedral intermediate collapses, the ethoxy group will get kicked out, and so that will now give us a methyl ester. It will give us a methyl ester plus the ethoxide. And so essentially what we're going to have is we are going to have an ester in the reaction mixture, which is different in identity from the starting ester. So we'll have like two different esters doing the reaction. So that's why the use of a different base is going to complicate the reaction also, because now this ester can get deprotonated to give you an enolate, and the starting ester can get deprotonated to give you an enolate. So both of those complicate the reaction, because you have two possible enolates in the reaction. And so that's why when we do the Claisen condensation, what we do is we try to match the base with the alcohol part of your ester so that we can get a clean reaction here. I hope you like the discussion. Bye.